There's only one thing which I want to mention more in a very very high level. I don't want to get into the proofs and other things. The guys who did the course last year actually had a guest lecture from somebody who works in this field and who was able to talk about another technique which is gaining a lot of popularity recently. So he talked about that in gory detail. In fact, he did some proofs from one of the papers that they wrote and so on and so forth. But unfortunately, I don't have the guest lecturer here this time, and it's also, I mean, just I'll introduce you the ideas to you, and then if you want, you can read up on those later, right? But in some sense, whatever we have done so far gives you all the tools that you need. It gives you the basic tools for you to understand more complex algorithms and so on and so forth. That's the whole idea for me to do this. And if you actually look at the book, right, the textbook, they almost in passing mention all of these algorithms. Right? I mean, they'll have like one paragraph saying, oh, this is how you do UCB, and this is how you do. They don't talk about median elimination at all. This is how you do something else which I will talk about in the next class called reinforce. Right? They mention these things in passing, and then they say, oh, we will build on some of these ideas as and when required for the full reinforcement learning problem. Right? So in some sense, the book treats bandits as something that is a necessary evil that you need to know about on your way to learning about the full RL problem. Right? Given the focus of the book, that's a valid way of treating bandit problems. But in fact, bandits itself is a very rich large literature, and it's a very active area of research for a lot of reinforcement learning people. And that's one of the reasons I actually covered bandits in a little more depth than I used to do maybe a couple of years ago. Right? So a couple of years ago I did bandits in like one class. Right, all of bandits. Anyway, so one thing which I want to talk about was Thompson sampling, which is gaining a lot of traction now. Okay, so it's more descriptively you could call it posterior sampling, depending on which literature you are reading. Some people call it posterior sampling, some people call it Thompson sampling. So the basic idea is the following, right? So I am trying to solve a bandit problem, right? And we know that if you know the parameters of the bandit, if I knew all the Q stars, right, I can solve it very easily, right? So what do I do? Take the highest, right? So what I am going to do when I do this kind of Thompson sampling approach is to take a somewhat a Bayesian way of looking at these things, right? I am going to say that, okay, I am solving this unknown problem, I am solving this unknown problem, but I am going to make some assumption about the parameters of this unknown problem, right? So essentially the assumption I am making here is about the Q stars. I am going to make an assumption that the true Q stars come from some distribution, right? I will start with some guess for this. The true Q stars come from some distribution, right? So if I know that my rewards are limited between 0 and 1, like many of the cases we have been assuming, the rewards are limited between 0 and 1. So what would be an appropriate assumption for this Q star distribution? Beta distribution. So people remember beta distribution? The guys who are in ML. Yeah. The guys who are in ML at least should remember the beta distribution. So the beta distribution is a distribution that is limited to 0, 1, right? And it can take all kinds of weird forms, right? And so this is typically a prior distribution that you assume whenever you have trying to find parameters of a distribution where the parameter is limited between 0 and 1. Okay, so the beta distribution is a very popular prior that is used. It's like that I make some kind of an assumption. Let us say that I don't know anything about the underlying problem, right? Then what will I assume? Uniform, right? You can assume a uniform distribution saying that I don't know anything, so my Q stars can come from anywhere. So now what do I do? And one way of solving this problem is to say that given my current knowledge about the parameters, which arm should I play okay, so that my reward is optimized. That is one way of thinking about it. So what should I do? Then I should take each bandit combination, right. I should say that okay the probability of, so q star 1 is some value, say 0.3, q star 2 is 0.5, q star 3 is something else, 1.2, like that. So I had to make one bandit problem and then figure out okay what is the best term to play here, right? And then take another bandit problem, figure out what is the best term to play, take another bandit problem, figure out what is the best term to play. And for each of these bandit problems I should look at what is the probability that this is the true q stars according to my current knowledge about the problem. So if I start off with a uniform distribution, then everything is equally likely, right. So all arms can be optimal, all arms can be non-optimal, and so on and so forth. So I basically have to play at random, right. But it turns out that doing this computation can be very, very cumbersome. You can just think about it, right. I am asking you to figure out for each arm combination with what is the probability that the arm combination can occur, right. And depending on the nature of the probability distributions you are assuming, this computation can become very, very complex, right. So the posterior sampling idea is a way of approximating this computation. So what I do is the following, it is very, very simple, okay. I have some distribution over what my q star values will be, okay. I have some distribution over my q star values. So what I do is I draw a sample from that distribution, right. So let us say something like this. So my okay, so q star 1 I am saying it's something like this, right, and then that is q star 2, that is q star 3, you have another color, okay, good, 4 arms because I am running out of colors, right. So q star 1, 2, 3, 4, right, this is the current distribution I have. So I am assuming that the true value of q star lies somewhere in this range, right, and it is most probably this value, but I do not know yet, right, there is some uncertainty about what the values are. Now what I do is I draw samples. You remember we talked about drawing samples from Gaussians and other distributions. I draw samples. So I draw so basically, right, so this is basically my reward, this is my reward axis and this is the probability axis. I draw a sample for, that is one, that is another, that is another, right. So now I have a specific bandit problem where my q star 1 is this, q star 2 is this, q star 3 is this, and q star 4 is this. So I have taken this distribution, right, and I have drawn one bandit problem from this distribution, okay. Now I solve this problem, right, I basically pull arm 3 because arm 3 gave me the best value here, so I pull arm 3. Now I look at the actual reward I get for arm 3, right. So I pull arm 3 and let us say that my arm 3 reward is that, this is the actual reward that I get for arm 3, and now I go back and update this fellow based on this reward, right. So what do you think it should be? Okay, it will become narrower because this is I kind of reinforcing my original belief that this is the most probable outcome. So right, this will become my belief. Now this is my new distribution. Now again I try to sample. So the probability that I will sample a high value for the green arm goes down now because when I played the green arm I got a smaller value. So I keep doing this until my probabilities kind of converge to the true q stars. At the time when I sample a problem from there, I will most probably be sampling the true problem, right, the actual problem underlying that which I am trying to solve. This is called Thompson sampling or posterior sampling. So this is getting a lot of attention recently, mainly because people have been able to show that this can give you better regret bounds than UCB. Right, so this can give you better regret bounds than UCB, and therefore there is a lot of attention that is being paid to Thompson sampling approaches. The analysis gets really hairy, and in fact until recently there was no analysis of the Thompson sampling approach, but more recently there have been several papers in the last 3-4 years. There have been several papers that have come up with new techniques for analyzing these kinds of algorithms, different from what we have been talking about so far.
Are there round based Thompson sampling algorithms?
It's kind of round based, right?
So what are usually one including at each time?
Yeah, we are not eliminating any arms, that is what you are saying, right? Well, it turns out that you do not have to, even without eliminating arms you are getting very good complexity, and typically what happens is after some time the posteriors become so focused, right? So the probability of you actually selecting the bad arm is gone. I mean, you do not really need to do a round based computation there, but yeah, I mean there might be a
maybe after few steps
room for, sorry?
after few steps that can be done.
After few steps?
That can be done, elimination.
Yeah, I mean, yeah, it's a possibility. So the only thing is, the only tricky part is once you do this kind of elimination, you have to come back and analyze it. So you saw how tricky this became, right? I mean, I gave you the right events to consider here, right? But to come up with these events is the tricky part, right? So once you come up with these events, it's easy to bound the probabilities, right? How do you know that this is the actual set of conditions that you should consider, right, for you to prove the result? So that is the tricky part. Now once I say that, okay, here is a round based Thompson sampling approach, then going and showing that it actually gives you the guarantees that you want becomes tricky. I mean, people, just the plain Thompson sampling without any round based thing itself resisted analysis for about a decade, right? And so it's not immediately clear, but there's more interesting results that have come in. Yeah, so people, I mean, there is a very old style algorithm, very old class of algorithms for solving bandit problems called learning automation algorithm. These are, so people know about finite state machines, right? All of you know about finite state machines. That you have a bunch of states and you have some input signals, symbols coming, and then you jump around the states and so on and so forth, right? So there is a class of finite state machines called variable structured finite state machines, variable structured automata, right? And people have used variable structured automata to solve bandit problems. I am not going to get into the details of it, right? So it's it turns out that some of what the variable structured automata algorithms are doing is posterior sampling. Right, it turns out to be very similar to posterior sampling, and very recently and earlier we knew results only for asymptotic convergence of this learning automation algorithms. So very recently, like late last year, October or November of last year, people have shown that they also satisfy regret bounds. They satisfy the log t regret bounds. So that, I mean, so a lot of interesting work that's happening in this space. And yeah, I mean, of course, yeah, you're welcome to try a round based Thompson sampling algorithm. I don't know, or just check on archive, right? The rate at which work comes out in this space, there might be something already out there. Okay, so I'll stop here. In the next class, we will look at ways of solving the bandit problem, which do not depend on estimating the value function. So everything we have looked on so far finds the function q, right, capital Q. So next class we look at one class of algorithms which do not look at maintaining the value function and directly try to learn the probabilities with which you have to select the arms. Okay.